So this is what the global network looks like today. It's a total of 130 stations. Don't worry about the difference between the stars, the points on this diagram, but this gives you a sense of the global distribution. Of course, what seismologists want is they want stations with equal station spacing around the globe. The challenge is the oceans, of course. We can put seismometers on the bottom of oceans. It's actually very difficult, and it's extremely expensive if you want to have it on the end of a cable. So if you want to have continuous data for long periods of time, you need to have the instrument connected to the internet, basically. So that means you need a cable. Cabled observatories are actually very expensive and very difficult to operate. So essentially all of these stars, all of these stations are in fact onshore stations, and so these are all located on islands. Okay? So that's one of the challenges, is filling these gaps. I like to include this. This map is now about 5 years old, but I don't want to update it because I just love this is showing the communications. Right? So 5 years ago, internet connections, they had internet connections at probably about 50% of the sites. Okay? So they were actually able to go from the site and connect to the internet fairly directly. There's a lot of other sites have VSAT, satellite communication, so a direct satellite connection from the sensor up to a satellite, and then of course the data back to a data center. But what I love here is, first of all, 5 years ago there were still some stations that would dial up. I think you had to call them to get data. Right? So you actually call the station to get the data. And even better, there are 7 stations where the data was sent by mail. As in, not email, as in snail mail. And so data would be recorded on disks and then would be mailed and added into the system. So today I don't think any data is sent by mail anymore. I don't think there are any dial-ups. Of course, all of them are now connected to the internet, although many of them still require VSAT-type connections. Of course, many of these stations are in parts of the world where there is not easy access to the internet. Okay, and so that network, global network of stations, is what we use to provide catalogs of earthquake activity on a daily basis. You can go to the IRIS. IRIS is the organization that runs the Global Seismic Network. It's this consortium of academic institutions in the US and around the world. And they operate this site, we call it Seismic Monitor, that's what this stands for. And it's just a nice, very nice graphic display that shows the current seismic activity. So that's why I'm showing that. So the point is that this is what the distribution of seismicity looks like. And now this is the kind of view that I, as a seismologist, need if I'm going to understand the earthquake process. Because it gives me fairly even coverage over the entire globe. It's not just showing me the earthquakes in places where there are people living, it's showing me all earthquakes everywhere around the globe. So we can start to understand the physical process, the physical mechanism behind these earthquakes. That's our objective here. If we want to mitigate earthquakes, we have to understand what causes them, and that means we need to be able to see into the physical process, not just when the physical process intersects with humans. So on this map, the purple dots show the seismicity for the past 5 years. Okay? So the purple dots are all of the earthquakes recorded for the past 5 years, and then the yellow, orange, and red are for the past 2 weeks, yesterday and today. This is actually, this is not today's map, but it shows that, so the circles show the more recent earthquakes. Okay? So now we're beginning to get that picture of where earthquakes are occurring around the globe. Do we see any patterns? Yes. What patterns? Yeah. So the comment was that there's a clear boundary of tectonic plate activity. So you're absolutely right, but we've not introduced plate tectonics yet, right? So just let's start by making an observation. Okay? What I want to do with today's lecture and tomorrow's and Tuesday's lecture, which is about plate tectonics, is go through the process of scientific discovery. Okay? And so the process of scientific discovery, of course, does not start with the final model. The process of scientific discovery is you go out and you make some observations, you try to wean out the bad data, and having made those observations, you come up with an interpretation, perhaps you come up with a physical model, and then you go and test that model. Okay? So that's the process. So you're right, you're absolutely right. The answer is plate tectonics. But before we get to that, let's develop that model, and let's start by making observations. So when we look at this map, what do we see in terms of the distribution of seismic activity? Yeah. So it seems to be strongest along island chains. When you say island chains, what do you mean? Okay. All right. So coming down Japan, around here, around Indonesia, coming past Australia, New Zealand. That's right. So the comment here was that there's these strong belts of seismicity along these regions. That's right. What other observations can we make? Yeah. They're occurring near the coast. So, for example, all down both North and South American coast. That's right. What else? Yeah.
On the darker side, there are more.
On the dark, so again, this is not today's map. So the dark part here is whenever I grabbed this snapshot, that was the dark part just represents where it was night at the time. So I was doing it during the daytime. So that's what the dark part means. And then your observation was that on this side of the map, they are what? Okay, so they're more near the mainland. Do you mean near the mainland or do you mean on the mainland? Oh, yeah, exactly. So over here, on this part of the map, there are a lot of earthquakes actually onshore. That is not true over here. So in the Americas, most of the seismicity is along the coasts. But over here in Eurasia, there's a lot of seismicity that is actually on the continent. Exactly. Yeah. Anything else? I think those are the main observations. Okay, so the observation is that, first order observation is that we see belts of seismicity. Okay, so there's a belt of seismicity along the North and South American coasts. There's a belt of seismicity along all of these island chains. And of course, there's also these belts or lines of seismicity you can see running through the middles of the oceans. Well, let's look at actually, it's not great, but if you look down the Atlantic, there's a line of seismicity down the center of the Atlantic. Okay, so we're seeing, so the seismicity is focused into specific belts. And then the secondary observation is that there are exceptions to this, and there are some places where we see seismicity. It's primarily onshore. Most of this seismicity is offshore, or at least along the margin. Okay, and this is obviously offshore. So this is onshore, and in this case where it's onshore, it seems to be more diffuse. It's spread out over larger areas. Okay, great observations. Okay, so the other observation to make is the association between seismicity and volcanoes. So here's another map that shows the earthquake distribution around the globe again. But what's also plotted is active volcanoes, what this figure is called young volcanoes, active volcanoes around the globe. And so we were looking at these belts of seismicity coming from Japan, around the Philippines, Australia, and New Zealand. And you can see that many of these belts of seismicity are also associated with volcanism. Okay? That's generally the case over here, around the sort of eastern half of the Pacific. Also here, sort of a bit of a deviation from that over here. It turns out the US part of North America is a bit of a special case. But there's also, so the point is over here through Africa. And here actually you can see nicely the line of seismicity down the center of the Atlantic. Okay? So again, so second observation is that in some places, but not all places, volcanism is associated with these regions where the seismicity. Yeah. Great question. Did you hear that? So when I say associated, is it a correlation or a causation? Right? So at the moment, we're just making observations. So this is a correlation. And so the next question, or question as we go down this, is there a physical mechanism that links these two, which would then suggest that there's a causation? Right? So a correlation is when you're just seeing that something correlates, is co-located in space and time. A causation is when there's actually a physical mechanism that's responsible for that correlation. So saying that there's a causation is a much stronger statement than saying that there's a correlation, and it is very important to understand the difference between the two. A lot of scientists will talk about a correlation, or they will see and describe a correlation, and then they will claim it's a causation. It's important to make sure we understand the difference between the two. Okay, so this ring of fire that we sort of started talking about, the Pacific Rim is also called the Ring of Fire. And it's called the Ring of Fire because of volcanoes. Much of the Pacific Rim has these volcanoes associated with it, and that's why it's called the Ring of Fire. And so there's no question that for a long time we've understood that there is this connection. And this Ring of Fire includes the Japan Trench. I'm going to explain to you what a trench is in a few moments, but the Japan Trench and other parts of the Philippines and down to Tonga, past New Zealand, these are the places where we have volcanoes. Okay? So there is this other process that's going on around this ring around the Pacific that is linking the two. Okay? All right, but so looking at the global seismicity map in a little more detail, this not only shows you the location, but it also shows you the depth. Okay, so a little more information. So the color scale, this is depth in kilometers. I'm sorry, I should say that there, but this is depth in kilometers. So all of the orange earthquakes are between the surface and 40 kilometers depth. Okay, and then through yellow, green, blue, purple, red, the red are the deepest down to about 700 kilometers deep. So that's the maximum depth of earthquakes that we observe in the Earth, is we see them down to 700 kilometers deep. Okay, so what do people see? What observations can we make about the depth distribution of earthquakes? Yeah. Okay, so most of the earthquakes seem to occur between 0 and 40 kilometers. Most of them are orange in color. That's true. Did you have one at the back? They are deepest in the Western Pacific, okay? So this portion here, the Western Pacific, is where we see some of, at least there are more deep earthquakes in the Western Pacific. There are also some, of course, over here, South America. What else? Oh, down here. Yeah. Okay. So what he said was, along the oceanic ridges, they appear to be shallow. What's an oceanic ridge? well, there you go. And I just want to make sure, okay, I want people to understand the process of making some observations, looking for correlation, and then looking for causation. Exactly. So the observation still here is that the ones that are along the middles of the oceans are all shallow. That's right. I'm not trying to be difficult here. I just want to make sure we all understand the kind of process of observations to model. Yeah. The deepest ones are seen in the trenches. I can see I'm losing this battle. That's right. The deepest ones are seen in the trenches. I did just show you a map that showed trenches, but that's right. So there are, in fact, trenches here. And I know that you are all required to cover plate tectonics in high school, in the high school curriculum, so you all know what's coming. But still, I want to make sure we understand the difference between observations, correlations, and then a physical mechanism. Okay, but so you've made the main observations here that there are some places where all of the earthquakes are shallow. And this is the best example in that this particular line of seismicity is all along the center of the Atlantic. And there are other places where we see deeper seismicity, okay? And so around the Western Pacific, South America, and Northern Pacific are places where we see that. And the other observation, of course, is that where we see, let's look at this case, South America, where we see deeper earthquakes, they're all offset with respect to the shallower earthquakes, right? So you can actually see the transition from orange to yellow to green to blue to purple in this transition here. And of course, they are not all plotted on top of one another. The deeper earthquakes are offset to the east with respect to the shallower earthquakes. So what's that implying? What's the geometry that's being implied here? And again, I'm looking for not an interpretation, I'm looking for a description of the geometry. Yeah. An angle, that's right. So it's implying that if you were to plot these up, you would find a plane, okay? So what you would find, if you were to plot these earthquakes in 3 dimensions, they would define a plane, okay? But that plane would be dipping. We talked about the dip of faults, okay? That plane would be dipping down into the Earth's interior because it's shallow here, and it gets deeper and deeper as you go further and further to the east, okay? Hopefully people can visualize that. I want people to be able to visualize what that looks like in 3 dimensions. Okay. So, all right, I will stop trying to hold back the whole plate tectonics interpretation. So what is the explanation for all of these observations? And the answer to that is plate tectonics. And so what is plate tectonics? So plate tectonics is a unifying theory that explains many diverse observations. So plate tectonics is really the game changer in solid Earth sciences, okay? And what I mean by that is that plate tectonics is a physical model, it's a physical process that we think explains many different physical observations in the Earth. It explains the distribution of seismicity that we've been talking about in great detail. It also explains the distribution of ocean bathymetry. Okay, there are shallow parts of the ocean and there are deep parts of the ocean, and it explains those. And it also explains magnetic stripes on the ocean floor, and it explains other observations as well. But these are the 3 key observations. And this single unifying theory explains these diverse observations. That's why we call it a unifying theory. And it's an incredibly powerful theory in the solid Earth sciences because it explains so many observations with a relatively simple model. So it should be the goal of every scientist to come up with a simple unifying theory that explains all observations. Right? That's the objective of science. That's the really big breakthroughs that people make. And what's really cool about this is that this is a relatively recent discovery. Relatively recent being the 1960s. But when you think about when the big discoveries were made in the various scientific fields, most of them were more than 100 years ago. So for solid Earth science, this is a relatively new unifying theory, okay, which is what makes it exciting. And just to kind of, so to show you the map, I said that it also explains the ocean bathymetry. So here is a map of ocean bathymetry. So the continents, the onshore pieces are all blacked out. Okay, so the color scale here is just showing you the depths of the oceans. And you can see various things. Well, you tell me, what are the main things that we see? Oh dear, it's only been an hour. What are the main things we see? Yeah. Say again? It's green in the middle of the ocean. That's right, I haven't quite hear. Yeah, so yes, so it's green and sort of yellow along these belts that we see that extend through the ocean, including, you will notice, along the middle of the Atlantic. What else? Yeah. The pink regions, right? Yeah. So you can see when you go around the margins of the continents, so again, remember that the coastline, when you look at North America, it's obvious, the coastline is shown black, right? So these pink regions, these are oceanic regions, but they are very shallow oceanic regions. So the area where the surface of the planet the solid surface of the planet is close to sea level, includes the onshore piece, but it also includes these broad regions around the edge. You'll notice that there aren't any, or it's very narrow along the western US, but there's these much broader regions along the eastern US. That's exactly right. Anything else? There's one other observation which is difficult to see, but we've talked about. You guys have talked about. Yeah. Very little of. Oh, that's interesting. So the Ring of Fire has very few ridges, right? So all of this region, there are no ridges. That's right. So the process that is associated, the physical process associated with the Ring of Fire is not the same as the process associated with these ridges. That's a great observation. That's exactly right. So what is the other bathymetric observation that we see associated with the Ring of Fire? Yeah. Excellent. Thank you. There's some very deep areas. It's difficult to see, but you can see these purple lines. They're lines because they're very narrow regions, but these are very deep parts of the ocean. Okay? So those are the key things that we observe. First of all, we see these kind of broad blue patches of the ocean. These are what we call the abyssal plains. These are the sort of wide expanses of the deep ocean, and they're at about 5 kilometers depth. There are then what we call ridges, shallow ridges, in fact, these sort of very long mountain belts that extend along wide portions of the oceans. And these shallow ridges are typically 2.5 kilometers deep, right? So they're only half the depth of the abyssal plains. And then finally, there are these very deep trenches. You can see one also along South America here, and then off the Aleutians, coming around off Japan, and then coming down here just north of New Zealand. These very deep sections of the ocean, what we call trenches, and they're up to 11 kilometers deep. So they're almost twice as deep as the abyssal plains. So very deep portions, okay? And so, well, just to finish today, of course, the point is that this is now plate tectonics, and plate tectonics is a unifying theory. It explains multiple observations, and so it's obvious at this point, but so this ridge that we see of shallow bathymetry, average depth 2.5 kilometers deep, down the center of the Atlantic, it corresponds exactly to where the earthquakes are located, all right? So these two things are connected with one another. And then these regions where we see these deep earthquakes going from shallow to deeper to very deep earthquakes, these actually correspond with these regions where we have trenches. So at the surface is a trench, and then we see seismicity extending to very great depth. So these things at the moment, these are still a correlation I'm pointing out to you, but plate tectonics, which we will talk about in detail on Tuesday, is then the physical mechanism, the process that actually explains this correlation. Okay, I will stop there. See you all on Tuesday.